Hello students, in this video I'm going to answer to all those questions of this chapter work, power and energy. This is one of the chapters of physics of AHSEC first year. So today I'm going to answer those questions which were asked in AHSEC first year final examination under Assam Higher Secondary Education Council, which were asked from 2023 to 2025. That means I'm going to answer the questions PYQs of last 3 years, 23, 24, 25. Okay, so before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. that's my Insta ID. You can follow me on Insta. Okay, now let's start. So in inelastic collision, so the correct option is only momentum is conserved. Okay, right? Total energy also conserved, but that option is not given here. Okay, here the options are only momentum is conserved, only kinetic energy is conserved, both momentum and kinetic energy conserved, neither momentum nor kinetic energy conserved. Here you see kinetic energy is not conserved. Okay, so that's why this C option is wrong. Neither momentum nor kinetic energy is conserved. Kinetic is not conserved, that is correct, but this momentum is not conserved, that is wrong. So that's why D is wrong, right? So only kinetic energy is conserved, that is also wrong. Okay, so correct option is only momentum is conserved. So total energy is also conserved, but as it is not mentioned here, so this option will be correct. Okay, so now let me answer the next question. So the gravitational force between two bodies is conservative, non-conservative, attractive and repulsive. Now you see gravitational force is conservative, we know that, but here you see regardless the path, you know the definition of conservative force, that the work done by the force, that means conservative force means if the work done by the force is independent of the path, then the force is called conservative, right? But here in this question actually we are asked to answer the nature of the force. It is either repulsive or attractive. Okay, so though it is not mentioned, we should understand that. Okay, so gravitational force between two bodies is always attractive regardless of its path between the two objects. Okay, so that's why the this is the answer, attractive. This option is correct. Okay, so now let me answer the next question. Unit of spring constant. Okay, so now you see unit of spring constant. Now you see, suppose you have a spring mass system. This is a spring. So here we have a mass on a surface. So when you apply a force, this is applied force, then a restoring force comes into play. That restoring force comes into play. Let it be Fs. That means spring force, which oppose the motion, or which acts in the direction opposite to the applied force, and which is equal to, according to Hooke's law, minus kx. X is displacement from this mean position towards left or right. Okay, so therefore the applied force will be plus kx. Okay, therefore k will be Fa by x. Force is Newton and displacement is meter, so unit must be Newton per meter. So correct option is B, right? Hope you have understood this. Now let me take the next question. Two bodies of mass m1 and m2 have same kinetic energies. What is the ratio of their momentum? Okay, they have same kinetic energies. Okay, so hope you know the relation between kinetic energy and momentum. So now you see kinetic energy is equal to half mv square, right? Half mv square. So if we multiply, instead of writing k, let me write it k only to represent kinetic energy. So if you multiply 2 and m on both sides, then it's gonna be equal to m square v square, right? And m into v is momentum, so 2 into mass into kinetic energy, that's gonna be momentum square. So that's why we can say momentum is equal to root over 2mk, right? Suppose now we have two masses m1 and m2, and their kinetic energies of both are equal, so let it be k. Okay, so therefore, so what will be the ratio of their momentum? Okay, so kinetic energy, momentum for this mass m1, that will be suppose p1 root over 2m1k, and for the mass m2, kinetic energy will momentum will be according to this relation, p root over 2m2k, right? So if you find the ratio p1 by p2, okay, then what will be the ratio of momentum? So that will be root over m1 by root over m2, right? So how to write the answer? So let me write it properly. So just I have explained this. Now let me write the ratio properly. Okay, let me write the answer properly. Okay, how to write that answer? Just give me a second. Okay, now you see. Okay, let's have space. Okay, now we know that relation between kinetic energy and momentum P is equal to root over 2m into k, where m is mass. Okay, so now you see, let us consider that let kinetic energy of mass m1 and m2 be k. Okay, as both have the same kinetic energy, right? So now you see, what is the ratio of their momentum? So momentum of m1 divided by momentum of m2. Okay, momentum of m1 by momentum of m2 is equal to momentum of m1 means, let me write here p1. Okay, and momentum of m2, let it be p2. Okay, so equal to root over, according to this relation, 2m1 into k by root over 2m2 into k. So therefore, let me write here, therefore p1 by p2, so here root 2 by root 2, root m1 by root m2, root over k by root over k, these are cancelled, only we have root over m1 by root over m2. So p1 is to p2 will be equal to root m1 is to root m2. So this is the required ratio. So this is the required ratio. Okay, so that is the answer. So hope you have understood this. Now let me take the next question. So this was asked in 2024, these two questions. Okay, so that kinetic energy, final kinetic energy minus initial kinetic energy is equal to work done, where the symbols have their usual meaning. So now this is actually work energy theorem, right? Here it is given to prove this only. Okay, it is not mentioned for conservative for variable force or constant force. So we can prove it for constant, either constant force or variable force. Okay, if it is not mentioned, then you can do whatever you want. So let me do it for constant force. Okay, so let me take a new page. So this is what we are to prove. Okay, now let us suppose let an object of mass m be moving along a straight line with initial velocity suppose u, okay, and a force F is applied along the direction of motion which produces acceleration A, and as a result the velocity of the object becomes v after a time interval t, suppose after a time interval t. Okay, let me consider that way. Okay, we know that work done by the force, so let me mention here, this is suppose constant force. Let me mention here, this is suppose constant force. Let me mention here constant force. Okay, work done by F on the object is W is equal to force into displacement, right? Force into displacement. Okay, force into displacement. Here S is the displacement of the body in time t, right? Let me take that. So now here you see W, force, we know that mass into acceleration, right? Mass into acceleration. Now let it be equation number 1. And we also know that so hope you know the equations of motion. So v square minus u square is equal to 2as. Hope you know this relation. So from here what you can write, a into s is equal to v square minus u square divided by 2, right? So this is suppose 2. Now if you use if you use equation number 2 in 1, then what you will get. So before I proceed, please pause the video and note these things, because I'm gonna clean this slide. Okay, so hope you have noted this. So now okay, let me scroll the page. Okay, now using 2 in equation number 1, what we're gonna have, W is equal to M into, instead of AS we're gonna put this value. Okay, so V square minus U square by 2, which gives half M V square minus half M U square. Now U is the velocity of the object before the force F is applied, and V is the velocity after the force F is applied after time t. So that's why this is final velocity and this is initial velocity. That's why half mv square is final kinetic energy, half mu square is initial kinetic energy. You know this is expression for kinetic energy, right? So this is nothing but kf minus ki. So this is proved. Okay, this implies this, where kf is equal to half mv square, that means final kinetic energy. And in exam don't write in short form. Okay, write kinetic energy completely. Ki is equal to half mu square, that is initial kinetic energy, right? So that's how we can prove this. So hope you have understood this. So next question is, what do you mean by elastic and inelastic collision? Let me answer this question. A collision between two bodies, is said to be elastic if both the linear and linear momentum and the kinetic energy of the system remain conserved. Okay, so to be elastic collision, the linear momentum and the kinetic energy of the system must be conserved. Okay, so now inelastic collision, now you see a collision is said to be inelastic if collision between two bodies is said to be inelastic if the linear momentum is conserved but not the kinetic energy. Let me write the answer. So a collision between two bodies, let me write here two bodies. Okay, here also I forgot to write two bodies. Okay, is said to be inelastic if the linear momentum of the system is conserved but its kinetic energy is not conserved, then it is said to be inelastic collision, right? So hope you have understood this. Now let me take the next question. Next question is, so that the total mechanical energy of a system is conserved if the forces doing work on it are conservative. Okay, that means we need to prove total mechanical energy of a system is conserved. That means that remains constant, okay, during the work done by conservative force. So let me prove this. This was asked in 2024. So we know that work done by a conservative force is negative gradient of potential energy, which is given by W is equal to minus del V. Okay, that means change in potential energy, right? So this is suppose equation number 1, and according to work energy theorem, according to the work energy theorem, let me write it properly. Work energy theorem W is equal to change in kinetic energy. Let me write is work done is equal to change in kinetic energy. So in exam, don't write only KE, write completely kinetic energy. Okay, so therefore we can write that work on W is equal to change in kinetic energy. Let me write it del K. Okay, del K. So now you see, this is equation number 2. So from 1 and 2, what we can write, that minus del V is equal to plus del K. So let me transfer this to on the other side, this minus del V on the other side. Then here we're gonna have del K plus del V is equal to 0, which means del K plus V is equal to 0. So here that means net change in energy is 0. So here K plus V means kinetic energy plus potential energy, and del K plus V means change in kinetic energy plus potential energy. That means this kinetic energy plus potential energy that represents mechanical energy. So here we have got, therefore, change in mechanical energy is 0. So change in mechanical energy is 0. What does it mean? That means mechanical energy of a system remains conserved, it doesn't change, right? So that means, therefore we can say that kinetic energy plus potential energy, which is total mechanical energy is constant. That's how we can prove this. So hope you have understood this. Now let me take the next question. So now an object of mass 1 gram is falling, this was asked in 23, okay, falling from a height 1 kilometer, hits the ground with a speed of 50 meter per second. Calculate the change in kinetic energy. So let me answer this question. So in the question it is given that an object of mass 1 gram is falling from a height of 1 kilometer and hits the ground with speed of 50 meter per second. So we need to find the change in kinetic energy. So that is the question, right? So now you see, when it is falling from the height of 1 kilometer, okay, so that means just before it is allowed to fall, its kinetic energy must be equal to 0. Okay, initial kinetic energy. that initial kinetic energy, first let me write what are the given things. Here height is 1 kilometer means 1000 meter, right? And what we have, its final velocity with which it hits the ground is 50 meter per second. Okay, when it hits the ground. Okay, so initial kinetic energy and mass of the object is 1 gram, so that means 1 into 10 to the power minus 3 gram, 3 kg. Okay, 10 to the power minus 3 kg. So initial kinetic energy that must be equal to 0, right? Initial kinetic energy is 0, and final kinetic energy that's going to be half mv square, which is equal to half into 10 to the power minus 3. V is 50, so we're going to write 50 square here. Okay, 50 square, that must joule, and half 10 to the power minus 3, 50 into 50, so let's divide it by 2. It's gonna give you 25, and 50 into 25, 1250, 10 to the power minus 3 joule, that's gonna be equal to 1.25 joule. So change in kinetic energy, therefore change in kinetic energy is del K is equal to final kinetic energy. So this is the final kinetic energy, this is initial kinetic energy. So final kinetic energy minus initial kinetic energy, so which is going to be equal to 1.25 minus 0 joule, that's going to be equal to 1.25 joule. So this is your answer, right? What is the next question? So express power as the product of force and velocity. Express power as the product of force and velocity. Okay, let me show you how to. That means we need to show this. Okay, so let me take a new slide. So this is what we need to show. Okay, so now you see solution. We know that power is equal to rate of doing work, dW by dt. This is the rate of doing work, right? And work done is equal to force into displacement. We know that work done is equal to force into displacement, right? So since work done, so let me write this one this way. Since work done is equal to force into displacement. Okay, so dW means small amount of work done when a body is displaced by very small distance, that is dx, when F force is applied, right? So that is the work done dW, right? So this is force into displacement. Okay. Force into displacement, right? So now we know that dx by dt, that is nothing but velocity. So let me write here this is nothing but velocity, or you can write instead of x you can write r as well. Okay, f dot dr. So dr by dt is velocity. Okay, so you can write this way. So if the object is not moving along only x-axis, then you have to write this way, w is equal to f dot dr. Okay, so if it is mentioned it is moving along x-axis, then we used to write f dot dx. Okay, so here this velocity is dr by dt. Okay, So this is what we need to prove. So that is power is equal to dot product of force and velocity. So this is nothing but velocity. This is velocity, right? This is velocity. So okay, this is force into displacement. Write it properly. Let me write it properly. Just give me a second. This is let me write here. Force into displacement, right? So that's what we can write. So now let me take the next question. So what do you mean by one-dimensional collision? Consider an inelastic collision. Find out the loss of kinetic energy on collision, and considering an elastic collision, find out the velocities of the bodies after the collision. Okay, now let me answer this question. So one-dimensional collision is an interaction between two or more objects where their motion is restricted to a straight line, making it a head-on collision. So one-dimensional collision is an interaction between two or more objects where their motion is restricted to a straight line, okay, making it an head-on collision. Let me explain it in a simple way. Suppose you have two objects, okay, they are moving in along a straight line. So it's moving with velocity u, it is moving with velocity v. Let us suppose v is greater than u is greater than v, such that it is moving faster than the second object. First object is moving faster than the second object, and it will collide it from the first one will collide the second from this side, from the left side, okay, and they are moving in the same straight line. And after collision, if they continue moving in the same straight line, along the same straight line, then this kind of collision will be called head-on collision, and which is one-dimensional. Okay, so now let's come to the next part of the question. What is the next part of the question? Consider an inelastic collision. Consider an inelastic collision and find out the loss of kinetic energy. So let me show you how to find the loss of. Let me take a new slide here. Okay, so now let me consider this is object. This is an object which is moving with velocity u. Suppose this is moving with velocity u, and there is another object, it is at rest. Let us suppose it is at rest. That means its velocity is 0. It is moving with velocity u, right? So its mass is suppose m1. Let me take its mass is m1, its mass is m2. Okay, and this object, suppose it is going towards this m2, and these two objects collide. Suppose these two objects collides. Okay, these two objects collides, and after collision they stick to each other, and they move together with velocity v. Suppose we move together velocity v. So if they stick to each other and move together with a velocity, then we used to say this is perfectly inelastic collision. Okay, so now you see. Okay, let me write what I have considered. So here you can see we have considered two bodies A and B of masses m1 and m2 respectively, and this first body, this A, moves with velocity u along a straight line towards m2, which is already at rest. Okay, it is moving with velocity u in this direction, and they collide and they stick to each other. These two balls A and B, they stick to each other. This is ball B. Okay, and then they moves together with velocity v. Okay, right? So here I have written, let us consider two bodies A and B respectively of masses m1 and m2. First body A is moving with velocity u and along a straight line towards B, which is at rest. Assuming the collision is perfectly inelastic, so in case of perfectly inelastic collision, the colliding body should stick together, and they should they must stick to each other, and they should travel with the same velocity, and that velocity we have taken here v. Okay, as shown in the figure. So here you see, according to the conservation of linear momentum, according to the conservation of linear momentum. Now you see, before collision, what was the total linear momentum? Momentum of body A, which is whose mass is m1, the mass into velocity is u, and before collision, momentum of ball B, body B, whose mass is m2 and moving with velocity 0 because it was at rest. Okay, and after collision, they stick to each other, so m1 plus m2, this is the mass of the combined body, so m1 plus m2, and they together move with velocity v, right? So that's what we have got. So from here, what we're going to have, m1 u, and this is going to be 0, is equal to m1 plus m2 into v. That's what we're going to have. So now you see, let it be equation number 1. So let me write this properly. This is p. Okay, let me do one more thing. Let me simplify it as a value of v. Okay, let me express this as a value of v. V will be equal to m1 u by m1 plus m2. So let it be equation number 1. Let me take this as equation number 1. This is equation number 1. Now let me copy this equation and let me take a new slide. Okay, so here is the new slide, right? And let me redraw the diagram. So okay, this is the diagram. Okay, we have already drawn in the previous slide, so I have copied the diagram and placed here. So here you see, as it is inelastic collision, there must be a loss of kinetic energy. So before collision, what is the kinetic energy? So kinetic energy before collision, So kinetic energy of the body, that must be half m1 u square, right? m1 u square, and that of the body B, that will be 0, which was at rest, so no kinetic energy. Then that's what we're gonna have, right? And that is equal to half m1 u square. That is what we have got. Now you see, after collision, kinetic energy, so let me write here I, that is kinetic energy before collision, initial kinetic energy. Now kinetic energy after collision, let me write as a kinetic energy, final kinetic energy. Okay, that's going to be half into mass. Here mass is m1 plus m2, as the two bodies combined to form a single body and moving with velocity v, so here v square. So now you see what we can do here. Okay, so from equation number 1, v can be replaced by this value. Okay, so that's why if you replace this v square, let me write half m1 plus m2. Now replace this v by this value, then let me copy this and let me paste here. Okay, this is what we're gonna have. As you can see, we have v square here, so we should give here square. Okay, so which can be written this way as well. Let me show you. Okay, you can write this way. Just give me a second. m1 square u square, and this is whole square. So if you cancel this one, and here square will be gone, so we have here m1 plus m2. So therefore final kinetic energy, that's gonna be equal to half m1 square by m1 plus m2 into u square. That's what we're gonna have. Okay, now this is the final kinetic energy. So here you see, this is initial kinetic energy, right? So what will be the loss of kinetic energy? How to find that? So let me copy, let me write here. This is initial kinetic energy, K E I is equal to what we have got, half m1 u square, right? m1 u square. Okay, let me copy this and let me go to a new slide. Okay, so this is the initial kinetic energy, and let me copy this final kinetic energy expression as well. So what now here you see, this is the expression for initial kinetic energy before collision, and this is the kinetic energy after collision. So now you see, though I have said there is a loss of kinetic energy, so let us check mathematically is that correct or not. Okay, let me check before we calculate the loss of kinetic energy. Let me show that kinetic energy before collision was is greater than the kinetic energy after collision. Okay, let me show that one first. Okay, so how to show that? First let me divide Ke final by Ke initial, that means final kinetic energy by initial kinetic energy, and if you divide, then what you're gonna have, let me take this expression here, this kinetic, this is the expression for final kinetic energy divided by expression for the initial kinetic energy, half m1 u1 square. So here u1 square gone, right? So then half gone, right? And m1 cancels m1 square, so which gives 1 by, sorry, there must be a m1 because there was m1 square, 1 m1 is cancelled by m1 plus m2, right? So here you see kinetic energy final, Ke final, m1 by m2, sorry, m1 plus m2 into Ke initial, that means before collision, kinetic energy before collision. Now you can see that definitely m1 plus m2 is greater than m1, right? Since m1 plus m2, that must be greater than m1, right? Because you see, this is m1, if you add something with m1, then that sum must be greater, right? Okay, right? Suppose m1 is 2 kg, if you add m1 plus m2, if you add some mass plus 1 kg suppose, then that's going to be definitely greater, right? So hope you have understood this. Okay, now you see, if this m1 plus m2 is greater, which is the denominator of this fraction, right? So now you see, in case of fraction 2 by 3 suppose, here denominator is greater than the numerator, so in that case it must be less than 1. Okay, it must be less than 1. Suppose here you can say, suppose you have a number, suppose this is 6 and here 12. So let us multiply a number which is less than 1 with 12, so let it be 0.5. So 0.5 into 12 is equal to 6. Now you see, so here this number is less than 1, 0.5 is less than 1. So in that case you can say 6 is less than 12, 6 is less than 12. Okay, so why 0.5 is less than 1? Because 0.5 means half, and here 2 is greater than 1. So you can compare this half with this fraction, right, where the denominator is greater than the numerator. So that's why this m1 by m1 plus m2, that must be less than 1. Okay, that must be less than 1. So now you see, if this is less than 1, so here you can see, from here it is clear that 6 is less than 12, right? We know that 6 is less than 12. So when you multiply a number which is less than 1, when a number is multiplied by a number less than 1, okay, by a number less than 1, then the product whatever be the product, that will be less than the original number to which one was multiplied by a number less than 1, right? Okay, so hope you know these things. These are very simple things. Okay, so let me clean this. So here, from here you can see, as this is less than 1, so this must be less than this one. Okay, you can compare this one with 6 is equal to 0.5 into 12, right? So 12 is greater, so here ki is greater. I am giving this as an example just. Okay, 6 is equal to 0.5 into 12. Okay, just an example. Okay, so we can say that final kinetic energy is less than the initial. That means kinetic energy before collision is greater than the kinetic energy after collision, right? So that's why we can say this is greater. So therefore, loss of kinetic energy, how to calculate the loss of kinetic energy? Loss of kinetic energy, how to find that? Kinetic energy initial, which is greater before collision, and kinetic energy after collision, right? So kinetic energy before collision is half m1 u square minus after collision is half m1 square by m1 plus m2. Let me write this one here, m1 by m1 plus m2, right, into u square. Okay, so hope you have understood this. And from here we can take common half m1 u1 square is taken common. Then within bracket what we're gonna have, within bracket we're gonna have this part is taken common, so we're gonna have 1 here minus, so half is taken common, m1 square means m1 into m2, so 1 m1 is taken common, so that's why here we're gonna have instead of m1 square, here there was a square, so 1 m1 is taken common, so now we don't need to write this square. Okay, so by m1 plus m2, right? Okay, this u square is taken common already. So now you see what we can do. Let me copy this last step and let me go to a new slide. Let me take a new slide. Okay, let me copy this last step. Just give me a second. So this is what we have got, right? And now let me simplify this, half m1 u square, and this one after taking LCM, m1 plus m2 minus m1 divided by m1 plus m2, right? Here minus m1 plus m1 cancel, so we end up getting 2 into m1 plus m2, right? Let me write it properly, 2 into m1 plus m2, m1 into m2 u square. So this is the loss of kinetic energy. So hope you have understood this. Now let me see the next part of the question. Just pause the video and note these things. Okay, so what was the next part of the question? Let me check that. Okay, here you see, considering an elastic collision, find out the velocities of the two bodies after collision. Let me find that one as well. Now let us consider, this is an object, this is a body A, this is another body B. Okay, this is A, this is B, and this one is moving with initial velocity u1, and this is moving with initial velocity u2 along the same straight line, okay, in the same direction. And consider that u1 is greater than u2, so that A can collide ball B, right? And they collide each other. Okay, they collide each other. This is this is object A, this is B. Okay, and after collision they move with velocity along the same straight line, move with velocities v1 and v2 respectively. Okay, let me consider that way. This is A, this is B. Okay, and mass of A is m1 and mass of B is m2. Okay, m1 m2, let me consider it. Okay, so what we have considered, let us consider two bodies or two balls. Let us consider two bodies A and B, two bodies A and B, okay, respectively of masses, sorry, M1 and M2, moving with velocities U1 and U2. U1, let me write here, U1 and U2 respectively, this is U2, okay, let me write it properly, U2, this is U1, okay. Respectively along the same straight line, and mention one thing, that U1 is greater than U2, okay, right, and they collide each other and after collision they move with velocities V1 and V2 respectively, along the same straight line, okay, okay, right, we have considered all this. Now let me copy the figure and let me take a new slide, pause the video and note all these things what I have considered. Now let me paste the diagram here. This is the diagram. This is before collision, and during collision, and after collision. Right. After collision they are moving with velocities v1 and v2. Now you see, as it is elastic collision, so total kinetic energy conserved and total linear momentum is also conserved, okay, according to the conservation of according to the law of conservation of, let me write here properly, conservation of linear momentum, what we can write, that before collision what was the total momentum of ball A or body A, that must be m1 u1, and that of B is m2 u2, right, m2 u2, and total is, how to find the total, just add these two. Then after collision m1 v1 plus m2 v2, right. So this is the momentum of A and this is the momentum of B before collision, and momentum of A and momentum of B after collision, right. Hope you have understood this. So from here what we can do, now let me bring this to this term to this side. Then what we're gonna have, m1 u1, right, m1 u1 minus m1 v1 minus m1 v1, and on the other side m2 v2 minus m2 u2 minus m2 u2. So this term is transferred to this side, right? So if you take m1 common, then what you're gonna have, then you're gonna have this term, right? Just give me a second. Then you're gonna have this on the left hand side, and on the other side if you take m2 common, then what you gonna have on the right hand side, you're gonna have this result, right? Sorry. So this is what you're gonna have, right? So now you see, let me give this is equation number 1. Okay, now so for elastic collision, kinetic energy is conserved. So that's why total kinetic energy before collision, let me write the term properly. So before collision, kinetic energy of the object A, that's going to be half into A1 U1 square, and kinetic energy of B, mass of B, that is M2, velocity of B, that is U2, initial velocity, so U2 square. On the other side, after collision, mass of A is M1, so half M1, then velocity of A is V1, so half M1 V1 square, then that of B half M2 V2 square. That's what we're gonna have. Now again, if we simplify, if we bring this term to this side and that term to other side, this term is transferred to other side, and this one is brought to this side. Okay, then what we're gonna have, then we can write this half m1 u1 square minus half m1 v1 square. Okay, so that means we have rearranged this equation in such a way that we get the terms consisting m1 on the same side of the equal sign, that is on the left hand side, and terms having consisting m2, we have got those terms on the right hand side of the equal sign. Okay, hope you have understood this. And from here we can take m1, half m1 common, right? On taking half m1 common, so we can write this in this way. Taking half m1 common, we have got this, right? And here we can take half m2 common, and doing so, what we're gonna have, we're gonna have this, right? Sorry, so this is what we gonna have. Okay, so let me just copy this, let me give this is equation number 1. So now let me copy equation number 1 and 2, and let me copy this to equation, and let me take a new slide. So here you see this is equation number 1, and let me copy the equation number 2 as well. Okay, you don't need to repeat these equations, as I have changed the slide. I don't want to go back to the previous slides again and again, so that's why I have written these two equations again. Hope you have understood that. So now if you divide 2 by 1, okay, let's divide equation number 2 by 1. Okay, so then what you're gonna have, equation number 2 divided by equation number 1. So on the left hand side, what we're gonna have, first take the left hand side of equation number 2 divided by the left hand side of the equation number 1. Okay, then on the other side of equal sign, take the right hand side of equation number 2, then take the right hand side of equation number 1. So this is what we have got, right? Okay, now you see half m1, so u1 square minus b1 square, that's going to be, you know, using a plus b into a minus b formula, that is a square minus b square. So u1 plus b1 into u1 minus b1, that's what we're going to have, and m1 into u1 minus b1 is the denominator, right? And on the other side of equal sign, so here you see it can be written as here half m2, and here we have b square minus b2 square minus u2 square, that's going to be b2 plus u2 into b2 minus u2, right? That's what we have got. Okay, divided by m2 into b2 minus u2. So we can cancel, this one will be cancelled by this one, m2 gone, this one, and m1 gone, right? And on both sides we have half, so we can divide both sides by half, right? Or you can cancel the half here as well in equation number 2, then you don't need to write this half. Okay, so hope you have understood this, right? So as a result, what we have got, let me rearrange these things. So as a result, what we have got, so on the left hand side we have got m1 b1 is equal to, on the right hand side we will get on the left hand side we have got u1 b1 here, b2 u2. So this can be written this way, just so it implies u1 minus u2 is equal to b2 minus b1. Okay, so this is what we have got. Okay, now you see here, this is called relative velocity of approach and this is called relative velocity of separation. So if in the question it was asked to find so that the relative velocity of approach is equal to the relative velocity of separation, then you have to prove this. But here it is not asked in that question, so just let me do one more thing. So let me simplify this equation. Let me express this equation as a value of b1, as a value of as a value of b2. Okay, in order to find the value of b1. Okay, so let me copy this relation, and here is the new slide. Let me write this one here, and let me write the equation number 1 and 2 as well. First let me cut these two things, half cancel, so we can copy this equation number 1 and 2 in this way. So here you see these are the two equations, 1 and 2. So what we can do here, you see, you don't need to repeat these equations again and again. So from here let me write b2 as a let me express this equation as a value of b2 in terms of u1, u2 and b1. So here what we're going to have, u1 minus u2 plus b1, that's what we're going to have. This is equation number, suppose 3. Okay, that's what we have got. Now if we use this equation number 3 here in equation number 1, that means if we replace this v2 by this value, then we will get v1. Okay, so using 3 in equation number 1, so what we're going to have, let me copy this equation number 1. This is equation number 1. So now this v will be replaced by this result of equation number 3, this one, right? Hope you have understood this. Okay, so using 3 in equation number 1, so this v2 is replaced by this result. Okay, hope you have understood this. Now here you see minus u2, sorry, just give me a second. Now you see on the right hand side what you can write, this is minus u2, that's going to be minus 2u2. So now let me multiply this one with all these two terms. Okay, here minus u2, that's going to be 2 minus u2, and then you multiply m2, so we got this, and after multiplication or after opening these brackets we have got this result. Okay, hope you have understood this. Now as we are to find v1, let me write the terms containing v1 on the same side of the equal sign. So if you transfer this minus m1 v1 to other side, that's going to be plus, right? So if you transfer this term m1 v1 on the other side, then it can be plus. So here we have m2 v1, so m2 v1, so we can write here m2 v1 and transfer these two terms on this side. Okay, then what we're gonna have, m1 u1, here m1 u1, then this is m2 u1, that's going to be minus m2 u1 now, minus m2 u1, just give me a second, minus m2 u1. Okay, and this is minus, that's going to be plus, so just give me m2 u2 is equal to this. That's what we have got, and from this term we can take v1 common. On taking v1 common, we gonna have this plus m1 into v1. Okay, hope you have understood this. We have taken v1 common, right? Okay, so from here we can find v1. Okay, so let me do one more thing. From these two terms we can take u1 common, and taking u1 common, what we're gonna have, we're gonna have this, just give me a second. So here you see, okay, so we can write this term this way, so u1 is taken common. Okay, now let me copy this last step and let me go to the new slide. Here you see, so this is what we have got. Okay, now you see v1 will be is equal to, let me write this one here, divided by, this term should be divided by this one, right? So here we have m1 plus m2 or m2 plus m1, same thing, m1 plus m2, that's what we're gonna have. So v1 is equal to, so m1 minus m2 by m1 plus m2 into u1 plus m2 u2 by m1 plus m2, that's what we're gonna have, right? Hope you have understood this. Now you see, this is the expression for the final velocity of the body A. Let me go back to the previous slide. Okay, here you see, so this is v1, we have obtained v1. Okay, now similarly we can obtain v2. You don't need to repeat all the steps. Here you see, in order to find v2 you have to express this equation number 3 as a value of v1. So v1 will be equal to v2 minus u1 plus u2. Okay, then you have to use this v1 here, but we are not going to repeat this process. Instead of that, we're gonna write similarly v2. So now you see how to find that v2. Let me show you. If you don't want to repeat the steps, and now you see, if you observe this pattern, okay, if you want to find the v2, just this, instead of replace the m2 by m1, okay, and m1 by m2. Okay, so here you see, let me copy this down. Okay. Now here you see, replace this u1 by u2, okay, and here m2 by m1, then m1 by m2. Okay, So now here you see m1 plus m2 or m2 plus m1, same thing, so we don't need to change here. Okay, right? Then plus again here you see in this term, in the second term here, what we need to change, we need to make it m1 and this should be made u1, right? So that means, let me show you something. So here this m2 is replaced by m1, this is replaced by u1. Okay, that's what we have done to obtain this expression for v2. Okay, so hope you have understood this. These two are the expressions, required expressions of final velocities. So thank you for watching. See you in the next video. Bye bye.